Okay, so a few things that came up after last week's lecture was on the preparation of alkynes. I think I gave you guys these examples that if we have a vicinal dihalide and we use an excess amount of a very strong base like sodium amide, we can do a double dehydrohalogenation, a double elimination reaction. One thing I didn't really show you is that there is an intermediate here where one halogen is eliminated with one hydrogen, and then the second equivalence takes that vinylic halide and does a second elimination on that. But there is something a little bit more interesting that happens if we're running this elimination on the production of a terminal alkyne, which is sodium amide in excess will not leave us with an alkyne, but will actually leave us with this alkyne nucleophile. Why? Because the same reagent that deprotonates the alkane to create a vinylic halide that sodium amide does one equivalence of deprotonation, one equivalence of elimination to give us this first alkene, and then it runs a second equivalence of elimination, and it leaves us with this terminal alkyne, and that same base, sodium amide, that is the base that we use to deprotonate our alkynes. Which means if you're trying to synthesize an alkyne, a terminal alkyne, and you use an excess amount of sodium amide, you don't have an alkyne. You have an alkyne anion. So on active, I think there's a problem similar to this. Although I can't exactly remember if it's the starting material you need to predict or the final product. And it gives you sodium amide in excess followed by H3O plus. What's that H3O plus step for? Yeah, it reverses that undesired deprotonation step. If you can't avoid it, then just fix it later, right? So an excess amount of a strong base to form a terminal amide, it actually deprotonates that terminal amide that you just made. Not what you want, but you can't get around it. So after you deprotonate, reprotonate. Step 1 leaves us with this alkyne anion. Step 2 puts the hydrogen back on. I had a run-in with my OChem 2 professor about a mechanism that had something like this. The last step of a reaction was a deprotonation step after the final product had formed, and then we had to show acid reprotonating it. And I went to her and I said, this just doesn't make sense. Like, why would I show deprotonation of a hydrogen just to reprotonate the hydrogen? Can't I just ignore those two steps that are just undoing each other? And she said, no. You lose points because you're not understanding that this is how the chemicals actually behave. And I sometimes agree with that. I understand. This is the actual process of how this alkyne forms, and it's important to recognize how you would go into a lab to get around this. On the other hand, I sometimes will ignore this. One way that I can ignore this is just by saying 2 equivalences of NaNH2, which means I do not have enough equivalences to deprotonate after the alkyne forms. Or I just won't say excess. I'll say use sodium amide to form the alkyne. And then we kind of ignore the fact that in reality, it's very hard to form the alkyne without also deprotonating the alkyne. So that's one thing that I wanted to bring up. Now, the other thing is this worksheet that we have today. You might notice that this worksheet is a bit all over the place. I wanted to start us off by practicing multi-step synthesis with some of the reactions that we have learned so far. By the way, what reactions have we learned so far? Just broad class reactions. Alkene addition. We know how to start with an alkene and end with new functional groups. Alkyne addition. We know how to start with alkynes and get to new functional groups. And alkylation. We finally learned alkylation, which is taking an alkyne and extending its carbon chain, alkylating the alkyne. So I want you guys to start off with this multi-step synthesis problem. Here's a skill that I want you guys to develop. 3 steps in solving multi-step synthesis. First, map your carbons. We've been practicing this skill. Remember that mapping your carbons is not just the same as counting. No, sorry. I'm just kidding. Of course. Mapping your carbons is different than just counting. What does mapping need? 2 structures. You map the carbons on one onto the structure of the second. The second thing, after mapping your carbons, brainstorm. What reactions are possible? What reactions wouldn't be necessary? And what reactions could work but probably aren't the best reactions to use? That means look at the functional group that you have at the beginning. Think about reactions you could use there. Look at the functional group you form at the end. Think of the reactions that you have learned to form that functional group. You guys might remember that I encouraged you to make a table of reactions where you map the starting material of what you formed to the functional group that you, the starting materials functional group to the functional group formed. That's the thought process in brainstorming. Look at what functional group you make and recognize what reactions you have to make that functional group. Look at what functional group you have at the start and recognize what reactions you have to work with from there. And then the last skill is working forward and backwards. And that's actually the same idea with brainstorming. It means don't think you need to solve this synthetic route by taking the starting material and converting it into the intermediates until you wind up with the product. Look at the product and think about what it could have started from. Sometimes that makes it easier to realize what your starting material needs to go to. You can solve a synthesis completely backwards. That would be called a retrosynthesis. I have what I want, and I just keep building it backwards until I get what I started with. I would encourage you to do these in groups. I want to spend maybe the next 8 minutes working on this. Groups is a great way to collaborate on looking through notes and brainstorming together. I'll be coming around to kind of pick your brains as well and give you some nudges in the right directions. 8 minutes till about 5. Let's go until 5:25 working on this synthesis.
Wow. You say we could use the other reaction. Right.
Would you like to join a group? Okay.
But then if we did it again, well, no, because we'd have to change that to a triple first. That's something different. So you're thinking to. Oh wait. No, I see what you're saying.
Are you suggesting you know what this can be made from?
Maybe.
Yeah.
Maybe.
Then that is your working backwards.
Start there and then go back.
And then you might be able to see a clearer path of how to take the starting material to get towards there.
Okay. Maybe we don't. That's a good idea. Because this one is.
Oh wait, yeah. Wait. How do we do that?
I did not get to watch the lectures. I know.
Oh, that's okay.
You
You might feel a little lost.
So
Yeah, it's okay. Then it's good that you're leaning on with some classmates to do this.
If we're changing it from an alkene to an alkyne, would that be one of the intermediates?
We're thinking step one, make an alkyne. I guess there's two steps here, but the only way I remember how to like flip it to zig-zig is to make that an alkyne and then like.
It sounds like you're saying you know the precursor of the final product. You know that this can be made from an alkyne.
Yeah.
Do you know a way to take an alkene to an alkyne in one step?
I was looking at my sheet.
Yeah, actually, these are all reactions with alkynes. So you'd actually want to look back to preparation of alkynes. Flip that sheet over. Now, look at all the ways that you make alkynes. What do you notice about all of our starting materials? Close.
Oh, no, not down here.
We can be, no, not at the bottom though. Not at the radicals.
Oh, right.
Halogens?
How many halogens? Do they all have the same number of halogens? Is there something on the board that might show you how to make alkynes?
Yeah.
That one.
Right.
That was a good intro. I'm seeing I'm seeing the vision. Okay. We'd separate that bond. And that would just be one of our intermediates?
I'm not sure what you mean by separate. You want to cleave a carbon-carbon bond? Because we can do that with ozonolysis of the alkene. Do you want to perform ozonolysis and cleave the carbons?
Well, wouldn't that allow them to move afterwards?
Well, think about mapping. Do the carbons need to move?
No.
It's the same two carbons in the beginning that are in the alkene that end as the same two carbons in the alkene. But we need to change the stereochemistry of the alkene. So I don't think I ever want to break that carbon-carbon bond.
Just move that.
Wouldn't it be nice to just be able to move hydrogens? Takes a lot of energy. You got to break those bonds. You're working forwards. Have you tried working backwards? Yeah? Think about the nature of that functional group you see and a reaction that we can use to make it. Is there, you wanna take the CH electrons and give them to H?
Yeah.
Does H own the electrons in a CH bond? How would we know? Right. Who's more electronegative? Carbon is more electronegative. So in those bonds, carbon owns the electrons.
I don't know how to go.
Also, your arrows didn't indicate the formation of a new pi bond either. It just pulled out all the electrons. But actually, this is a good precursor. If you know that an alkyne can be used with Lindlar's catalyst to make this cis alkene, Now you have a precursor. So the question is, what molecule is needed to make an alkyne? What functional groups do we need as a precursor to alkynes? It looks like you've added 2 bromines, but you haven't done anything with the pi bond, right? So that's not a reaction we've learned.
No, it's broke the laws of chemistry.
Absolutely. And if you can do it in a lab, you'll be hired by every richest company in the world. So think about how you can get to that alkyne precursor. I think you've lost a carbon. Yeah, you've got a 5-carbon chain here and a 5-carbon chain here, but only a 4-carbon chain here. If those are the carbons you want it to be at, there's multiple ways you could extend it. You have added a carbon and also put the alkyne now with that new carbon. Okay, but if you look at the positions your carbons are in, 2 and 3 are the alkene, 2 and 3 are the alkene, this would be 1 and 2. So maybe we can draw it so that, so now 2 and 3 are also the alkyne. Good. Now the only improvement here would be straightening the alkyne so that it represents its linear geometry and there's no zigzags going through it. So Sarah, have you worked with your group to talk about why an alkyne would go well there?
No.
What do you guys think?
Other reactions we've been looking at, similar kind to alkene
Alkene to alkene.
Yeah.
Do we know any reactions that can form an alkene? You're just going to have that triple bond come straight down. Yep. 1, 2, 3, 4, 5. Yeah. So long as you count this as carbon 1 is methyl, carbon 2, 3. Perfect. You could make it longer if you wanted to as well. So yeah, you're still working on one. So New, you said, what if the alkyne comes first? Sarah is saying, what if the alkyne comes right before the final product? Sarah, do you have a reagent that tells you you can take an alkyne to a cis alkene?
I'm just thinking that like one of these carbons goes.
I think Yvonne's got one. Not in front of you? You don't see the formation of a cis alkene? Yeah, we can use an internal alkyne with Lindlar's catalyst and we can make a cis alkene. That would be the final step, right? Alkyne to the cis alkene. So that is a working backward step. I know how to make a cis alkene, Lindlar's catalyst on an alkyne. Now the question is, how do I make an alkyne? What is our precursor to alkynes? Not this. Actually, these are all reactions with alkynes. These are ways that we prepare alkynes. So if you still have this side, Yvonne, too, yeah. We're looking at reactions that prepare alkynes. What do those all have in common? Nope. These are ways that we can react with an alkyne. These are ways that we can make alkynes. They all have 2 halogens. They're all dihalides. Some are geminal dihalides. Some are vicinal dihalides. Add a bromine. Add 2 bromine. Do we have a reaction that takes an alkene to add 2 bromines?
in order to turn it into that. And then you get to a triple. We could be wrong.
It seems like you're saying, oh no, show me what you think forms there. How does adding hydrogen remove hydrogens? You're taking alkane and hydrogenating to remove hydrogens?
I guess that's where we're confused. Like, are you saying you can go forwards and backwards with these? Or they only
Oh.
one direction?
They are one directional. That's a good question.
Yeah, because these are only addition, right?
That's correct.
Yeah.
These are not
We're
elimination
not given
reactions.
any elimination.
And what you're showing is an elimination. Actually, you have elimination pathways. Is that not elimination? I'm pretty sure I put it on your Unit 4 test.
Yeah, that's what I was saying. Like when we were talking about, like I feel like we should use that to get it to a triple bond.
If you want an alkyne intermediate, then you need to make an alkyne.
That's what I was saying.
In order to make an alkyne, I'm just going to flip this over for you. We looked at how to make alkynes.
Yeah.
We said that alkynes need to start from two types of functional groups, geminal dihalides or vicinal dihalides.
Yeah.
Those are our alkyne precursors. So you guys did the right step, which is you know how to make that final product, Lindlar's catalyst. How do you make the alkyne from there? You need to make a geminal dihalide, or a dihalide. Now the question is, how do you get there from an alkene? Yes. Perfect. And this is, yeah, that's exactly right. Oh, actually, because it's not terminal, it's never going to get deprotonated, so we wouldn't need the H3O+. That's another reason why it's just a little more convoluted than it needs to be. Great job. Perfect. Are there any other reagents you could have used in that first step? You put Br2. Could have put Cl2. I2. Yep. Yeah, you want to show the reagents that get you there. Yep. But that's, yes, that's the intermediate we want.
Oh, right on. Okay, good. Because that was just.
The question is, how do you get there from the alkyne, or from the alkene starting material?
Disappear, so excess of something?
So is this one halogenation?
Yes.
Okay.
Yep. First step, halogenation.
And then
And Maisie, what you're wondering about is actually on the board up there. Second step is elimination, dehydrohalogenation, twice. Is there? No. What's the excess under the arrow? Here? Yeah. That you have excess amount of base. Yeah, just excess Na. Meaning like it's not a 1-to-1, it's not a 1-to-2, it's not a 1-to-3, it's excess. Okay. You've got a lot of NaNH2. Indigo, you want a sheet? Okay. Yep. Okay, let's pull it all together. Great work there. I want to ask you if you see the value in mapping. Do you know why I encourage you to map your carbons? Not a bad idea to make sure you don't lose any carbons during your intermediates, because that is a way to lose points on a test, is to draw an intermediate that has too many or too few carbons because you just weren't being careful about your carbon structure. But there's another insight that mapping your carbons gives you. It can tell you whether you have structural rearrangements that occur. For instance, carbons 2 and 3 were my alkene. If I suddenly got some reactivity going on at carbon 4, then I might suggest there's a carbocation intermediate that is rearranging to that tertiary position. The other thing it tells me is whether I do any bond cleavage, like ozonolysis, whether I do any carbon-carbon bond formation, like alkylation. It tells me whether my carbon chain grows or shrinks. And then it also reminds me that carbons 2 and 3 are going to be the only place that chemical reactivity is going on. I don't want to see any reactions at the methyl group. I don't want to see any reactions at the tertiary group. I want to make sure that my reactions just keep me here. Now, a lot of you got here very quickly saying that I can make a cis-alkene one way if I have an alkyne intermediate and I react it with hydrogen and Lindlar's catalyst. Do you guys remember what Lindlar's catalyst was? Yeah, me either. It's just a bunch of chemicals that poison the reactivity of the alkene so that the alkene does not hydrogenate. Now this is where I saw a lot of you start getting tripped up saying, I'm not quite sure how to make that alkyne, or at the very least, I don't know why there'd be another step. Some of you tried to show that the alkene can go directly to the alkyne. There are some enzymes that can do things like that. There are enzymes that can pull two hydrogens off of a carbon chain. But in terms of organic chemists, that's actually a very challenging thing to do, because you need to keep some of the electrons from those bonds to go into a new carbon-carbon bond. But you also need to take some of those electrons out, because that's too many electrons. And hydrogen doesn't like to take electrons from carbon, and so dehydrogenation is very hard. Taking two hydrogens from here to here, not something that you'll see us do in this class. Instead, the way that we form alkynes are from geminal dihalides and vicinal dihalides. And since we know that carbons 1 and 2, and by the way, you could have mapped these differently, could have numbered it the other way, so long as they're mapped the same. We know that carbons 2 and 3 are the positions I'd want to have either a geminal dihalide or a vicinal dihalide on. We have worked backwards. Now it's time to work forwards. Can I make a geminal dihalide on position 2 or position 3 from my starting material? A geminal dihalide? No, because my starting material has an alkene between 2 and 3. So I can do an alkene addition reaction, but there is no alkene addition reaction that will move the hydrogen from one position to the other and add 2 new halogens to that position. All I can do is halogenation, Br2, rather than a geminal dihalide. Jackie, what does this give me? Vicinal dihalide. Good. Those were both good possibilities there, but this is the only possibility that can be made. So alkene addition to dihalide to alkyne, we need an excess amount of sodium amide. If you gave me NaNH2, full points. If you gave me NaNH2 in excess or in 2 equivalences, full points. I did see one person put first NaNH2, second H3O+, just like we put up here, which wouldn't actually be necessary in this case, because the internal alkyne can never be deprotonated. You don't get an alkyne anion from that internal alkyne. I probably still would have given full points because you're recognizing something we just put on the board. But this is a good time to clarify. This will never get deprotonated and make a terminal alkyne that needs the acid workup. There's a multi-step synthesis. Great work. This is, truth be told, a much longer multi-step synthesis than what I normally give you on a unit test or on an exam. But being able to solve something like this, being able to draw from the reactions you have, to react with alkynes, to prepare alkynes, to react with alkenes, those are all important things that I want you to know how to do. All right, here is another multi-step synthesis I'd like you guys to try your hands at, and there are 2 routes to get us there. Actually, you know what? I think I'm going to show you 2 routes, but they actually end up with structural isomers. So feel free to pick one route and try solving it. Oh, no, yeah, okay. Two different structural isomers, two different routes. But the way to get any isomer can be solved two different ways as well.
That's what, is that what you said? You could do either because you could use HX addition twice, or you could halogenate and then hydrogenate.
Well, HX addition gives you what type of product? HX twice gives you HX once gives a vanillic halide.
Yeah.
HX twice gives geminal dihalide.
Oh, okay. But they're not.
And they're not geminal.
Yeah.
Yeah,
Okay.
that's the important
So it's
distinction.
The halogenation would be the vanillic one.
Well, halogenation, vanillic is when it's an alkene and the halogens.
Right.
So HX once
We'll do
gives you one vanillic
one
halogen. X2 once gives you two vanillic halogens.
Okay. That makes sense.
So
You want to do the X2. Right?
You want HX twice, right?
Oh.
No, HX twice.
Geminal, right?
Oh.
Yeah.
So we would want to do the.
And geminal is when they're off the same carbon.
Yes. Yep.
And then but the halogenation you just do it once. So because we only have one box, we want to do the halogenation.
So would that, and then how would you get to the final product?
So would halogenation be in the last step, right?
Good question.
Step
Oh, that
before
makes
it
sense.
should be the whatever, right? Am I on something?
Yeah, you're onto something. Keep talking with your group. I never gave you a structure that long. Did I? No, that was the homework.
This is the homework. I was trying to draw it out of my head.
Sorry. Yep.
No, because
That's my bad.
Because I kept being like one carbon off every time
Oh
I tried to
no.
make it. I was like, where the hell is this carbon? So
That is my fault.
forgot that was good.
This actually forms this. This is a perfect route, but it gives this stereoisomer. This route actually gives this stereoisomer. Remember that halogenation is an anti-addition. Okay. Okay.
Yeah, sorry.
Good.
Sorry, I missed it. Sorry. Sorry to forget.
Not a lot of communication at this table. You're all doing your own thing. New year off to a good start. Do you want to try and collaborate and see if you can share your thought process with them to see if they agree? Oh, sorry, what? You got too many carbons in your structure there. And now you've mapped your carbons incorrectly.
Because these are in 2 and 3 position.
Well, and these are in 2 and 3 position as well. If it's an excess, do we get this?
No.
Right.
This is excess.
So what would we want? One, yeah, just one equivalence. And do you see a route from this intermediate to the final product? Do you, no. You don't see a route?
Well, I'd assume that this is snapping two H's, right?
Yeah.
So it'd be halogen.
Halogenation adds halogens.
Hydrogenation.
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 And would hydrogenation, would we be doing hydrogenation of an alkene or an alkyne? Right. Is that a syn addition or anti-addition? Yeah. So both hydrogens will add wedge,
Oh, well, this one would be anti.
which, well, this is anti, but if you did hydrogenation, you would get a syn addition product. So the route that you're actually on is for the formation of that stereoisomer.
Okay.
Nice. Keep going. See if you can convince Peter of where you're at.
Yeah, I think so.
At least why don't you share your thought process with him, see if you can get him to agree.
Well, working on the top.
Okay.
We think we have the bottom.
I agree. You do have the bottom.
We just need the top.
Yeah.
How do you get them on the same side? Because the ones that we have oxygen.
Oh, well, very different. Well, you can't. From this alkene, the only way to add two more bromines is...
What would be, but then they're on the opposite. Yeah, we need them on the same side.
Wait, can we do something like a cis alkene and then it'll like make it like it'll adjust itself?
If we
or
started
something?
it this way. Okay, so
That
one's we're kind of
Oh, H2 in Lindlar's catalyst does not give a trans alkene.
oh, man. So what
H2 in Lindlar's catalyst gives us cis.
and we don't
Sodium
have
in ammonia gives us trans.
Oh, so it's the sodium and ammonia.
Mhm.
Okay, alrighty.
Oh, and then
So-
this one would be because if you rotate it, it becomes it behaves towards and away. So zigzag to zigzag would make that look like that, right? So if
So-
you rotate just around this carbon.
No, actually this is already anti, and this reaction is anti,
Oh, so that is okay.
which means the alkene should be in this configuration. It should be a zigzag alkene, a trans alkene.
But this one
So
should
this
be-
alkene
should be zigzag.
would react with Br2 to give this.
Oh,
So this is
that one would be zigzag. I just moved that one. So would this one just be the hydrogenation? Just each.
Well, there's a lot of actually right answers. Both routes have two correct answers.
so
Oh, no.
So there's different combinations that you guys can use. It seems like you guys are on the route of hydrogenation first, then halogenation. Any reason you haven't considered halogenation first, then hydrogenation?
Because
No reason, right? So play around with the reagents that you have and play around with the order if you want to. You guys are on a good route. You've just got to get the right reagents to give you the right stereochemistry. Are you convinced, Aiden? Would you have gotten there?
Yeah, if I would have just stopped looking at, because I thought that this part was going to be different, not
Oh,
here.
okay.
So once I like not focused it on the second reactor.
That's important. I'm gonna share that, I think.
one
Sarah, that's 5 bonds.
Because she was saying
This can exist. There you go. Yeah, that's exactly it. Now there's another route for both products as well. You did hydrogenation followed by halogenation, but there's no reason you can't do halogenation for one of them. Actually, it might only be one. Sorry. But you could also do halogenation followed by hydrogenation to get to the product you want to. I think it is only one. Oops. Okay. Think you got it?
Yeah.
Good.
I hope so.
I'm in the process of
Okay, awesome. Oh, let me see yours. Nice. So basically the exact same reagents and just, oh no, slightly different reagents. Yeah, yeah.
Because this one's going from its internal.
Mm-hmm.
It's not from here straight to here.
Good. Perfect.
Okay.
Do you guys feel good?
Yeah.
Yeah.
What do you think?
Yeah.
Nailed it.
Yeah.
Great job.
Yeah, that made a lot more sense once we started
The stereochemistry of the alkene can be manipulated too.
considering. If you took that
So
around
you just leave it zig-zag
yeah, because it
and
was
just leave it what we thought was in
they go on.
This works, by the way. And this doesn't give us this.
So this one is the one. Is this one the H2?
Yeah, actually, sorry, this doesn't work.
Okay.
H2 with Lindlers doesn't react with alkenes.
Oh, okay.
You would just want H2 with palladium. Here, you want H2 and Lindlers to give you a
Okay.
cis alkene.
Okay.
So what have you guys decided on?
Well, we were trying to figure out how to get the zig, but sodium dihydride,
Sodium in ammonia.
sodium in ammonia with excess makes the zigzag.
It's not
alkene.
sodium amide. That was something I brought up last week, which is they look identical. NaNH2 in excess does entirely different reactivity than Na, comma, NH3. It's kind of like, this was the example I gave, elemental sodium and elemental chlorine. Sodium will explode when it touches water. Chlorine will kill you, but sodium chloride, yummy, right? Sodium amide, very good base. Sodium in ammonia, a partial hydrogenation reagent. So we wouldn't need the excess, and it's not NaNH2. It's actually Na, comma, NH3. All right. Yes, this gives it to
It's
you.
good. Okay, so this one, like you were saying that we could halogenate, like we could start with halogenation.
Yep, and that
How
gives
would
you a,
attach that bromine.
well, Br2, it gives you a trans vicinal dihalide.
As an alkene.
Yeah, here, Elliot's got it right here. A trans vicinal dihalide.
Okay.
And then add the two hydrogens to be,
Okay.
oh, but it actually won't give it to you trans, it'd give it to you cis. So
Oh, this would be.
let's go through and solve these together, because you guys are right there. All right. Great work, everybody. These are really challenging. I love the way that you guys have been using the diagrams to look for the reactions. Again, this is the first time I've ever given these to a class, and it seems like they're becoming a useful tool for you, right? Now keep in mind when you prepare for the final, you don't have all that space. So think about the reactions you want to put on your cheat sheet. Think about the reactions you know already and you don't need on the cheat sheet. And think about how you can create your own diagram to take up space. But you build a table of reactions, you spend hours building that, you're not going to need some of these diagrams on your cheat sheet. All right, some of these have more than one route. Here's what I would say is, in this bottom route, I see halogenation with anti-addition. I know that halogenation is anti-addition, so if I have my carbon chain in the same shape, but I have an alkene between these two carbons, I can just run Br2. You know what? I wanted to take a step back. Sorry. One of the first thought process I saw you guys go through was, it's not HX addition twice, because HX addition gives geminal dihalides, not vicinal dihalides. It's not halogenation twice, because that gives tetrahalo products. So it must be some combination of halogenation once and hydrogenation once. One of the questions is, should I halogenate first and then hydrogenate second? And when or should I hydrogenate and then halogenate? And when I hydrogenate, should it be cis or trans hydrogenation? So the question is, halogenation first. This is in the brainstorming category of your synthesis. Hydrogenation first cis or trans hydrogenation. You can play with them and see what they all give you, all those different combinations. My instinct here is to say this looks like the anti-addition product of halogenation from a transalkene. And this looks like anti-addition hydrogenation from a cis alkene. So that tells me that I can get to these final products by doing H2 with Lindlar's catalyst on top. That gives me a cis alkene, reacts with Br2 by anti-addition, and rotates into a lower energy conformation here. Or I can do sodium in ammonia. Remember, not sodium amide. Very different chemical, very different reactivity. Gives me a transalkene that runs with halogenation to give that very obvious anti-addition product. But there is another way to get here too. In the first reaction on the bottom, if I ran halogenation once with one equivalence, I get an anti-addition dihalide, a vicinal divanillic halide. The halogens are both bonded to an alkene, and they're trans to each other. Now, if I run hydrogenation, that's just PD with carbon. Remember, Lindlar's catalyst is intentional to stop the reactivity of the alkene. So here I need to go back to my alkene reagent, H2 with PDC. This is syn. Oh, that's the problem, isn't it? Nobody's looking at me weird enough. I'm doing this for the wrong product. That gives me syn addition, which actually is what I wanted up here. PD2, Br2, one equivalence to the trans divanillic vicinal dihalide. And then H2 with PDC, which is syn addition. The two hydrogens add to the same face, dashed, and the two bromines add to the same face, wedged. There's not a better route for the second one. No matter what, halogenation will always give us that transalkene, and hydrogenation following that will give us syn addition. So there is no better route for the second stereoisomer. The top stereoisomer, though, has two routes where you switch the order in which you add them. What do you guys think? Interesting? Requires some amount of creativity, and yet some people will call that critical thinking. Do you think there's a difference between creative thinking and critical thinking? Two sides of the same coin. And maybe the thin boundary that separates critical thinking and creative thinking is what is possible. One thing that I heard somebody mention was, I know I want syn halogens up there, and the only reaction I see with alkenes that gives me syn addition is the syn diol addition. That's creative, and then the critical thinking kicks in to say syn diol will never be syn dihalide, right? Those are just different functional groups. There's nothing I can change about the chemical that makes syn diol addition give me bromines instead of alcohols. And then one thing that kind of clogs the creative thinking is getting too critical and saying, I think I know one step has to come before the other. I can only get one of these alkenes, and that's what I need to go with. The creative thinking says, I've got two different alkenes that I can get to. How could those two stereoisomers of the alkenes impact the stereoisomers of my dihalide product? Okay, so I want you to think about that. When you're in this class, you are doing a lot of critical thinking. This is a science class. And that should make you feel a little bit like an artist doing creative thinking. A lot of my colleagues agree organic chemistry can feel so elegant, a little sloppy at times, especially the way I draw it on the board. but very elegant with the way the chemicals transform their functional groups through reactions. Okay, why don't you guys take a 5-minute break? When we come back, we're going to look at some more reactions, some more mechanisms, and a little bit of nomenclature. All right? We'll come back at like 6:03, 6:05. Yeah. That's right. Okay. You have it on here. For the 5 minutes.
I was like reading through and it said one side.
Thanks for saying that.
So I just wanted to like clarify that it was both sides.
And you're talking about like on simple syllabus?
Yes.
Okay. I don't know why I would have left it like that because.
Yeah, it just has like exams one side only.
Okay. Thank you.
Yep.
I'll clarify it right now. Peter, I don't see it anywhere. You scroll through and try to take a look. Was it the midterm? It's the midterm on that front sheet of the midterm. I say you're about one side.
Oh, were you? Yeah, are you fine? No. Okay. Yes, I was surprised.
You know what?
I was like,
This was something at the beginning.
so if you're my mom's boyfriend.
I was like, oh, I know.
He's cool. Yeah, I guess Tim's right. But they were my mom's.
I'll say one-sided midterm, two-sided final. And I probably will get rid of this whole thing.
I know.
Just use the simple syllabus from now on. I know. I was really hesitant to use simple syllabus at all because I felt like I made a pretty syllabus on Word, and then they made me use this syllabus that I think is like clunky and ugly and very hard to navigate. No, I don't think the House is requiring HB. The House bill is not requiring simple syllabus. Simple syllabus was the college's way to navigate requirements around that. So other institutions have other requirements. This was how our college tried to navigate it. And it's not a bad navigation. It's just ugly. And it's not simple. Far from it.
Yeah, your guys' side is horrible. Try to navigate on yours.
Yeah. The editing is so unclear. You can create a master syllabus that then can be picked up by any of the individual sections within a course. I made a master syllabus for the 12-15 labs. And when I adopted it into my own specific course, it reorganized all of the different little sections. I was like, what's the point of a master syllabus if I don't have the control of where things go in the order? Doesn't make any sense. All right, now I imagine that as normal, I bite off more than I can chew, and we probably won't have time to get through all of what I have today. So I'm wondering if you guys want to save nomenclature for next week and do more reactions today, or if you want to do more reactions today, do nomenclature today and save some more reactions for next week.
I will say
Active can be pushed back.
no, I'm just saying like I feel like the reaction.
Okay. All right. You guys don't like nomenclature? Maybe we'll rush and get to it. Yeah, it's true. All right. Well, here on your worksheet, I've listed out a few more reactions. To be fair, these reactions I think are predominantly listed on the learning objectives sheet under unit, man, they all get lost in my head. Under unit 9 on alkynes, but some of them actually show up on your unit 10 or section 10. I have them listed on the learning objectives under section 9, but they show up on section 10 active. So a bit disorganized there. I'll try to fix it. Ultimately, though, all of the reactions that I want you to know are still listed on the learning objectives document. They're just not, they might not show up with the unit or the section homework that I said they would. All right, this top reaction on the left-hand side, what is our starting functional group? Right? Sorry. I froze because my computer said clear 50 gigabytes of storage, and I said, why 50 gigabytes? It's because I cleared my trash. I cleared my storage today, but I didn't empty the trash. So it's all sitting in my trash. Sorry. Alkane is our starting group. What reactions have we seen so far with alkanes? Zero. Alkanes are a product of alkene hydrogenation and a product of alkyne hydrogenation, but we have not taken an alkane as a starting material. Now, when we talk about reacting with alkenes, we have a pi bond that we can react with. And then we can put new groups like carbon-halogen bonds. And then we can actually do more chemistry by breaking those carbon-halogen bonds to make alkynes. And once we have alkynes, we have even more pi bonds to do chemistry with. The chemistry of an alkane is pretty inert. Those CH bonds are not very reactive. There's no other functional group. There's no other, there's no polar bonds. There's not a lot to do here. So this reaction that we're looking at is called radical halogenation. And if you wanted to be specific, this is radical halogenation of alkanes. To run radical halogenation, I need halogens and radical. Radical, well, of course. We're going to create the radicals using light. So underneath the arrow, I'm putting H nu. In some places, you may not see H nu written, but instead you'll see light. Do you guys know why H nu is the representation for light? The energy of a photon is equal to Planck's constant times the frequency of that photon. And this energy that's represented by H nu, this is typically ultraviolet light. Ultraviolet light will split open the bonds between the halogens. One thing I want you to notice here, don't use chlorine with this reaction. Chlorine is actually too reactive, whereas bromine is just reactive enough that we get regiochemistry. We talked about radical stability on alkane structures, and we said if a radical forms on an alkane, it will form on the most substituted carbon. That is where the radical is most stable. And so we see that here. The radical forms on the most substituted carbon, and so the bromine adds to the most substituted carbon. Could you tell me a byproduct of this reaction? Sorry? A bromine? A bromine? Just by itself? HBr. Where's the hydrogen coming from? Would this be classified as a substitution reaction? Substitute a hydrogen for a bromine. Absolutely. It's a radical substitution reaction, but it's definitely a substitution reaction. We're substituting a hydrogen, and that means we get a byproduct of HBr. The reason we don't use chlorine is that it's not regioselective enough, but bromine always adds to the most substituted position. That tells you, it has nothing to do with bromine, it tells you that there is a most substituted radical intermediate. I'm going to abbreviate that as most substituted carbon radical, carbon with an unpaired electron. I want to show you guys the mechanism for this reaction. I just wonder if you want to see it now or if you want to see it later. Now? All right. Flip your sheet over to the backhand side. We've got this radical reactions. And we're going to show this exact reaction, 2-methylbutane reacting with bromine in light to form 2-bromo-2-methyl-butane. In the initiation step, we'll show the bromine-bromine bond, and we'll also show 2-methylbutane. The 2-methylbutane doesn't have a reaction here, but I like to keep everything consistent. Radical reactions have very specific names, as opposed to the mechanisms I showed you for HX addition, X2 addition, acid catalyzed hydration, haloether, halohydrin addition. Those all had kind of generic names like acid base or protonation or nucleophilic attack. Radical reactions all share pretty much the same names. Initiation. Initiation is where you start with no radicals and you initiate radical reactivity. There's nothing that indicates to you that this will happen. It's just something that you need to know with initiation. Do you know what? I had some feedback from one of my students. I think it was an OChem 2 student who said, one thing that helps me understand my mechanisms so much better is drawing in all of the lone pairs of electrons in all of my species. And I said, good. Oh, it was the OChem tutor, Johnny, downstairs. He said, when I draw in my lone pairs, I understand it a lot better. Great. Draw your lone pairs. Take it from a tutor. The reason I don't draw lone pairs, it takes a lot more time. And I'm taking up a lot of time right now, I know. So, word of advice, if these electrons still don't make sense to you, don't hesitate to go in there and draw in all of those electrons. Okay, one question real quick before I move on. is what I have here drawn in red the same as this? Correct. It is the smallest detail, right? I don't want you to miss it. The way we draw our arrow indicates how many electrons we're indicating. A full-headed arrow, think of it as 2 hooks, 2 electrons. This is what we call a fish hook arrow, 1 electron. So make sure you're not drawing this, which, as Will said, is indicating that you have 4 electrons coming from a source where there are 2 electrons. Instead, we want to say that these 2 electrons go in opposite directions. These full-headed arrows are what we call heterolytic cleavage arrows. The electrons go in one of 2 directions heterolytically. They're not equivalent to each other. These are what we call homolytic cleavage arrows. The electrons go in both directions equally, the same amount in both directions, homolytic. All right, step 2 is propagation. At this point, I am going to draw out the CH bond to the most substituted carbon, because this is where the radical will want to react. Propagation in biology typically means life begets more life. I propagate my plants. Sometimes they survive. And usually that means I start with 1 plant and then I end up with 10 until they die. Propagation in radicals does not mean start with 1, end with many. It means start with 1 radical, end with a different radical. Initiation creates radicals. Propagation transfers radicals. That means one of these bromines will react as a radical, and the CH bond is going to go through homolytic cleavage. Hydrogen will take one of the electrons, and those 2 arrows will meet in thin air, which represents the formation of a covalent bond. 1 electron from each atom to create a 2-electron covalent bond. The other electron from the CH bond homolytically cleaves to the carbon. Now, this goes exactly against what I typically tell you. I tell you that bonds form from the more negative to the more positive, and when bonds break, they break to the more negative because they are the ones that own electrons. That's heterolytic cleavage, which does account for 90% of our chemistry. But this 10% is homolytic cleavage, and you actually see the electrons go in both directions. This gives us our byproduct of HBr. It leaves us with an equivalence of bromine radical, and we have propagated the radical from bromine to the carbon. What do you suppose happens to radicals in the final step, termination? No radicals create 2. 1 radical creates a different radical. In termination, 2 radicals react, no radicals at the end. So, our bromine radical that is remaining and our carbon radical that has been created, just like the Br and the H, these will create a bond right here in the middle between them. 1 electron from each atom comes to form the bond. You guys know how in general chemistry, this is sometimes how they teach you how to build Lewis dot structures. It's like take the dots around the Lewis symbol and share 1 dot from each atom to make a covalent bond. This is how some general chemistry teachers tell you to draw a Lewis structure. And it's rarely how bonds actually form. Again, like radical reactions account for 10% of the reactions we're learning. That's a very rare way for a bond to form. It's actually much more common that something donates both electrons to make the bond. I digress. Okay, there you go. We have now shown the formation of an alkyl halide from an alkane. Now that I have an alkyl halide, I can do all sorts of chemistry. I might run elimination on this alkyl halide and get an alkene. I might run substitution on this alkyl halide and get some other functional group. I had an alkane at the start which couldn't do anything but burn, and now I have an alkyl halide which opens the doors for multi-step synthesis and reactivity. Cool? All right, let's go back to our worksheet. Our next reaction has an alkene intermediate, or sorry, an alkene starting material. Haven't we learned enough reactions with alkenes? No, of course not. We talked about this with the alkynes, and now I want to canonize it. Make sure that you understand this reaction is one I want you to know. When we start with an asymmetric alkene, we can run anti-Markovnikov HX addition. Once again, our halogen here can be HCl or HBr pretty often. We already know how this alkene reacts with HX. That's an acid. The alkene is a base. You create a carbocation intermediate, and then the halide attacks. This is not enough. We introduce hydrogen peroxide, or really any peroxide. This is a radical reaction. So keep in mind that radical reactions behave by initiation, propagation, and termination. Can you guess what chemical here behaves as the radical initiator? The oxygen is, can you be a little bit more specific about the nature of the oxygen? Sorry, I wanted you to clarify what the oxygen is in. It's not like it's elemental oxygen O2. It's not like it's water or an alcohol, but it's specifically a peroxide. The oxygen in the peroxide is the radical initiator. Considering that this is the only change, alkenes with HX, Markovnikov HX addition. Alkenes with HX in peroxide, anti-Markovnikov addition. The difference must be the peroxide. Since we know that this has a radical intermediate, and we know that the radical must be on the most stable carbon, this is similar to what we saw with the alkynes. We know that the intermediate must actually add the bromine first and place the carbon radical in the most stable position before it reacts to add the hydrogen. Most stable carbon radical means bromine adds first. Just like how with normal HX addition, the most stable carbocation intermediate means the hydrogen must have added first. We're simply flipping the addition of the two groups on its head, changing the nature of the intermediate. Our next reaction is radical halogenation of alkenes. Although I like to call this allylic halogenation. Once again, we'll react with Br2 and light, but this time we're not in the presence of an alkane, we're in the presence of an alkene. So the most stable radical position is not on the most substituted carbon, it's on the most substituted allylic carbon. There are two carbons that are allylic. One of them is more substituted than the other. So just like last time, where I expect to place the halogen on the most substituted position, substituting the hydrogen at that position, here I'm going to substitute the hydrogen at the most substituted allylic position. Here's a primary allylic. Here's a secondary allylic. Where should I put it? The halogen. Which hydrogen should I substitute? Secondary allylic. So this is as simple as redrawing the structure and placing a bromine on that secondary position. Do you notice on this line you have a plus sign? Oh, it's kind of tiny, huh? But there is a plus there, which indicates that it's not just one structure that's drawn. What other product might be isolated during this reaction? HBr. There would be a byproduct of HBr. That's an important thing that we can show, but that's a byproduct. And here I'm showing that there's another major organic product that forms. If this forms an allylic radical, does that radical sit only on that secondary position? Radicals are conjugated. Conjugation means there's an uninterrupted series of p orbitals, which means there's a new molecular orbital that demonstrates the radical not on position 1, not on position 3, but on both position 1 and 3. We can only visualize this by drawing two resonance forms. Position 1, 2, 3, position 1, 2, 3. Do you guys remember doing this last week? We created allylic radicals. We showed their resonance. This is a reminder on the electron arrow pushing. Electron comes in, one electron comes in, one electron goes out. But Lewis structures are lying to you. There's none of this going on. Molecular orbital theory says it sits in an orbital that is shown, that is sitting on both carbons 1 and 3. So this resonance form reacts to give us this allylic halide product. But this resonance form gives us what? Can you show me the allylic halide that forms from the second resonance form? You can start with the same carbon chain, because we know the carbon chain won't end. You can keep the alkene in the same place from that second resonance form. It's missing your alkene. Got it. Alkene's in the right spot. Good. Well, it's not where the radical is, it bonds to that carbon. You've lost a carbon.
Gotcha.
So now you're going to keep the same carbon chain with the alkene in the same spot and add the bromine to that position. Yep. Line out. Yep. That's it. No bromine. Oh, you're right. Sorry. Okay, good. But where's the alkene? Oh, sorry. I'm so sorry. I'm looking at the wrong spot. So we're going to keep the same carbon chain, but now we're going to attach the bromine where the radical is. Yep, we want to keep this carbon chain, but you're not going to put the bromine there. That's a carbon. You're going to bond the bromine off of that carbon. Yeah?
And then what happens to...
Oh, you see how you lost a carbon? You had carbon 3, and now it's just a bromine. Carbon 3 bonds to a bromine.
Then you have to add?
Draw a line. Yep.
Doesn't matter what direction.
No, that would just be a conformational rotation.
Like that?
Sure. Nailed it. That's it. Got it. Good work. Yes. Perfect. You're going to keep this carbon chain, this one here, and off of carbon 3, draw a new bond. All right, here's one thing I don't want you guys to miss, because this is an easy way to lose a carbon in your structure. So I saw a lot of people that said, okay, the bromine is gonna add to position 3. So then they draw a bromine at position 3. Boom, carbon is gone, right? There's no longer a carbon there, it's now a bromine. So instead, draw that carbon chain exactly as your resonance form predicts, and off of that carbon, draw a new bond to the bromine. These are the two products that form. And I like to refer to them as 1,3 allylic structural isomers. 1,3 allylic isomers. And it's because of that allylic radical intermediate that forms. These don't necessarily form 50-50. They don't even need to form one major, one minor. They're just two possible products that you have to be looking out for in the reaction. All right, our next reaction takes us away from some radical chemistry and shows us some new ways to form alkyl halides. Oh, I didn't make the change that I thought I did. I am so sad and disappointed, and it's been a long day. So if you'd make a change for me, on these two alcohols, make one of the chiral carbons wedged and one of the chiral carbons dashed. I'm going to add the first one to be a wedged chiral carbon and one of them to be a dashed chiral carbon. The chirality of this reaction is relevant. Here we're going to show not the substitution of hydrogen for halogen, but the substitution of alcohol for halogen. We're actually going to come back next week to talk about more substitution reactions of alcohol to halogens. But for right now, these are what we consider the we're going to use some inorganic reagents. The other reagents we'll use are acidic reagents. So on this first one, let's see how we can convert an alcohol into an alkyl chloride. When we react this alcohol with thionyl chloride is SOCl2. The thionyl chloride will react with the alcohol leaving us with inverted stereochemistry at the chiral carbon. Alcohol is gone, chlorine is in. This should remind you of that backside attack that we saw with halonium ring reactions. Something was oriented one direction, something is now oriented the opposite direction. There are some cool byproducts here. One of them is HCl and the other is SO2. And by cool byproducts, I mean when you use this in the lab, be careful because it is toxic on its own and it produces toxic byproducts. And you get to use this chemical in the OChem 2 labs. You have to be very careful. Our next reagent converts the alcohol into an alkyl bromide. This is PBr3 phosphorus tribromide. And in the same way as the chlorine substituted anti to the alcohol, our bromine will substitute anti to the alcohol. So if your alcohol was dashed, your bromine is now wedged. So there's stereo-specific chemistry that's going on in these reactions. Stereo-specific. All right. The next set of reactions, you can see diverges things a little bit, correct? We're no longer looking at alkane or alkene or alcohol. We're now looking at dienes. So these reactions are all reactions with dienes. Can we be more specific about the nature of these dienes? Remember that dienes can be named as isolated dienes. The alkenes don't touch each other. Conjugated dienes, they're in an uninterrupted series of p orbitals. And cumulated dienes, where one carbon is a part of both alkenes. How would you describe the dienes you see on this set? Are they isolated? They don't, they have no chance of communicating with each other, the pi bonds? If we count for p orbitals, all of the carbons in the sp2, all of the carbons in the alkene are sp2, which means we have a p orbital, a p orbital, a p orbital, and a p orbital. That is an uninterrupted series of p orbitals, much like p orbital, p orbital, p orbital, conjugated system. This is 4 p orbitals in a row, conjugated system. An isolated system would need to have at least one sp3 hybridized atom separating the two alkenes. But since these alkenes are completely in series, these are conjugated dienes. That's important because isolated dienes will just go through alkene reactions the way that we know alkene reactions go. Conjugated dienes behave differently than normal alkenes. These behave uniquely. Largely, the uniqueness comes from the fact that molecular orbital theory says electrons are going to behave not as two separate alkenes, but as one continuous pi bond, and then also a separate orbital. It's very fun. Sorry. So what we're going to show here are those multiple equivalences of reactions. At the very top, let's look at HX addition at very low temperatures. So I'm going to show you HX at negative 70 degrees C. Ooh, chilly. You could actually run a reaction like this using liquid nitrogen as a way of cooling it. I think liquid nitrogen melts at like 76 degrees C, or that's carbon dioxide. So you can cool this type of reaction by having carbon dioxide, dry ice, or liquid nitrogen to help cool the reaction. Very cold conditions are what we call kinetic conditions. Kinetic means what? Anybody? What does it evoke in your mind? Motion, movement, that energy of moving around. What do molecules have very little of at negative 70 degrees C? Motion, movement, moving around. So we call this the kinetic product because it is the product that forms with just the smallest amount of movement energy. Here is the one equivalence addition of HX that we get. Maybe I should clarify one equivalence here. If I run HX addition, once again, one equivalence at higher temperatures. So let's call this hot. Boy, that's pretty vague. 0 degrees C can be considered hot relative to negative 70 degrees C. 100 degrees C might be considered hot compared to 0 degrees C. So this is a little bit vague. We're saying this has more energy than negative 70 degrees C, and we call this the thermodynamic reaction. A thermodynamic reaction will have the highest energy transition state, but also the most stable product. So I like to think of that as the dynamic reaction, the highest high and the lowest low. The product that we get here looks like this. What's going on? There was no pi bond there before. How did a pi bond come out of thin air? Did it? Did this pi bond come out of thin air? Because there was no pi bond there before either. Given the fact that we know pi bonds can move around in resonance, what do we know about this? Saying like this plus this. Oh, you're saying the... And keep the halogen here? Because if I drew the pi bond here, wouldn't that just be this structure, but flipped? How did these two structures form? They're related by what? By what? Not just the radicals, something about the radicals. The radicals are related by... Starts with an R. The radicals are related by resonance, which means the two structures form because of a resonance-stabilized intermediate. So how is it that I could go from doing HX addition across one of the pi bonds and not the other, And here, doing HX addition seemingly across both of them, but one of them rearranges, this product must be the product of a resonance form. If the pi bond has rearranged, that must be the result of a resonance form. When structures rearrange, like hydrogens and methyl groups and alkyl groups, that's a carbocation intermediate, just in general. But when pi bonds move, that is resonance. So this must have a resonance intermediate. So we're running out of time, which means we're not going to look at the other reactions. We'll come back to those. But now I'd like you to head to the bottom here where I give you kinetic and thermodynamic reactions. And I'm afraid I'll need to have you draw in a reaction coordinate diagram that I did not give you. This reaction coordinate diagram will have energy plotted along the left-hand side on the y-axis. But this is a two-way reaction coordinate. Most of the time that I've shown you reaction coordinate diagrams, we start with a starting material on the left, intermediates in the middle, products on the right. But this time, I want to give you the starting material in the middle and two intermediates going either direction to two different products in either direction. So let's start here with our 1,3-butadiene starting material. No. No, I'm so sorry. Tell me. Just where it says kinetic and thermodynamic reactions. You're going to have to draw this in. Yep. Is it what? Two-way reaction coordinate. Typically I can see that. Typically our reaction coordinates are one directional, but here there are two different products that can form, and so we're going to show those two different products. Now, this intermediate, you know what? I drew this really high. I bet you guys might have copied that. I'm going to need a little bit more space, so I'm actually going to draw this a little bit lower. And I'm going to show this intermediate moving to a higher energy reactive intermediate. And that reactive intermediate whoa, what's that? That's a resonance hybrid. Deal? The resonance hybrid is both resonance forms at the same time. On one side, oops, that should be just a solid line. That resonance hybrid might react as a positive charge on a primary carbon. Primary carbons are not as stable as secondary carbons when they hold carbocations. So that is a very high energy intermediate. But you'll notice that it comes down to form a very low energy product. And I apologize, I forgot to say this. Over this first arrow, we're adding HX. HX acts as an acid. The diene acts as a base. The less substituted carbon takes the hydrogen. That leaves a carbocation on my secondary carbon, which is an allylic carbocation. So it's not on the secondary carbon, it's in resonance. Here's that allylic carbocation. So one way that this allylic carbocation can react is if the positive charge localizes on the primary carbon and the alkene localizes in the center. The other way that this allylic carbocation can react is if the carbocation localizes on the secondary carbon and the alkene localizes as a terminal alkene. But this does not give us as stable of a product. Can anybody tell me why these products don't have the same stability? Can you name a difference between the two products? You have a more substituted alkyl halide? I'll tell you this, the carbon-halogen bond doesn't make the biggest impact in the stability of the molecule. What's the only other difference between these two structures? The substitution of the alkene. Can you describe the substitutions of the alkene? Good. Red is mono-substituted. Green is di-substituted. Mono-substituted is less stable. Do you remember we said this early on when we started ranking alkene stability? More substituted the alkene is, the more stable the alkene is. This is a more substituted, so di-substituted, which is more stable, lower in energy. Can you tell me anything about why the carbocations are different energies? Why is one carbocation high in energy and the other carbocation low? What do we know about carbocation stabilities? So this is a more substituted carbocation, which is more stable. And this is a less substituted carbocation, which is less stable. Which of these is the kinetic product, and which of these is the thermodynamic product? Remember, thermodynamic has the highest highs and the lowest lows. Green, our di-substituted product, our primary carbocation. This is the thermodynamic reaction. This is why this must be run, quote unquote, hot. You need to give that molecule enough energy to be able to access that high energy carbocation. And which of these is the kinetic product? The red, which means if you only provide just enough energy for the molecules to move, they will have only enough energy to overcome this lower activation barrier. They will not have enough energy to overcome the high energy activation barrier. Kinetic control at very low temperatures. Thermodynamic control at higher temperatures. Have a great Thanksgiving break. I'll miss you guys on Wednesday, but we will pick up with the rest of these reactions and our final section on Monday. 2 more class periods. Okay. Have a great break. I'll see you guys next week.